Hi, welcome back. This is Professor Ridge, and today's lesson is on section 4.1, polynomial functions and models. A polynomial function, P, is given by P of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2 plus, and then you continue in this fashion till you get a. So basically we're going descending order, and the subscript, notice a sub 1 matches its x to the first, and then a sub 0 is your constant term. Okay, so the subscripts are just distinguishing the coefficients. So a sub n minus 1, a sub n minus 2, those are the coefficients for the term that matches the degree, right? So a sub, if we had a polynomial, say 3x squared plus 5x plus 1, this is polynomial degree 2, and we write it in descending order, and a sub 2 would be 3. Okay, so the coefficient for the x squared term, so we denote that by a sub 2. The coefficient for the first degree term for x to the first power would be 5. And then the constant term, a sub 0, that's the same as x equals 0. Okay, so those are the coefficients. And they have to be real numbers. And then the powers, the exponents for all the variables have to be whole numbers. That's key too. Okay, so you need real numbers for coefficients, and you can't have any negative exponents or fraction exponents, right? Those things are not polynomials. Okay, so when we have this polynomial function and we have it, generally write it in descending order, not always, but generally. The first non-zero coefficient, a sub n, is called the leading coefficient. And note, it needs to be put in descending order or thought that way, whether it's written in descending order or not. The leading coefficient is the coefficient for the highest degree term. Term a sub n x to the n, that's called the leading term. So again, the highest degree is going to give us the first term. You put it in descending order. And of course the degree will be n. Okay, so let's look at some examples, and we're going to introduce some of the names for these. So a constant function might be something like f of x equals just a number, 7. Okay, so note, you can write 7 as 7x to the 0. Okay, so the degree is 0. The leading term would be 7, x to the 0, which is still 7, and the leading coefficient is 7. Okay, so that's a constant polynomial. A linear polynomial is degree 1, so f of x equals 3x plus 2. It's degree 1. The leading term would be 3x, and the leading coefficient would be 3. Then a quadratic polynomial would be degree 2, so fx equals negative 3/5 x squared plus 2x minus 7, so that's degree 2. Leading term is negative 3/5 x squared, and the leading coefficient would be negative 3/5. Then we have a cubic polynomial, so that's degree 3. So minus 5x cubed plus 2x squared minus 7x plus 1. So that's degree 3. The leading term is negative 5x cubed, and the leading coefficient is negative 5. And then we have a quartic polynomial that's degree 4. It should be f of x. F of x is, say, x to the 4th minus 8x cubed plus 11x squared plus 5. I'll leave out the x because I'm running out of room. But anyway, it doesn't matter. So the degree would be 4. The leading term would be x to the 4th. The leading coefficient would be 1. Okay, and then, you know, any degree higher would just say it's a polynomial degree 5, degree 6, whatever. All right. Now let's talk about the leading coefficient test. Okay, so it's the leading term test. Other books call it leading coefficient test. But here we're calling it leading term test. So if the leading term, if a sub n, x sub n is the leading term of a polynomial function, then the behavior of the graph as x goes to infinity. So that means as you get larger and larger and larger on the x-axis, on the x side, so as x gets bigger and bigger and bigger, or as x goes to negative infinity, so as it gets to negative 1 million, negative 2 million, so on. As x keeps getting more negative, it can be described in one of the four ways. So what we notice, if the degree of the polynomial is even, then we know that and the leading coefficient is greater than 0, positive, the ends are going to go, both of them are going to go up. So we're talking about the end behavior. In the middle we don't know, but both ends are going to go up. And then if the leading coefficient is negative and the degree is even, both ends are going to go down. And again, the middle, we don't know what's going on in the middle, but the ends are going down for sure. And then if the degree is odd, the ends are one's going down, so the negative side's going down, positive side's going up. That's if the leading term is positive. If the leading term's negative, it flip-flops. On the left side of the graph, it's going up. Middle, again, we don't know. And then the right side is going down. Okay? So you can kind of think of this as end behavior. Sometimes we refer to that. What are the ends doing? You know, what's happening as x gets extremely large on the positive side? What's happening as x goes to negative infinity? It's getting extremely negative. Okay, so the end behavior. Okay, so let's use the leading term test to describe the end behavior of the graph function. So if you were to graph this, right, on an xy axis, what are the ends doing? Now, since the leading term is negative x to the 6th, degrees even, and leading coefficient is negative. Negative. Okay? So if the degree is even, both ends are going up or both ends are going down. If it's positive, they go up. If it's negative, they go down. And what I do is I just think of the simple case, I just think of x squared. I'm pretty confident, you know, x squared opens up. It's a parabola that opens up. Negative x squared opens down. So I just think about that. Okay? That's the easy case. So the end behaviors, as x goes to negative infinity, the y value is going to negative infinity. This is the left end. Of the graph, right? And then the right end is doing as x goes to infinity, that's going to the right. As you go to the extreme right, the y value goes to negative infinity. Okay, so both ends are going down. Okay, if you can just draw the picture, that's fine. But this is the notation we commonly use. So instead of writing y, of course, you can use f of x. All right, let's try another one. F of x equals, say, 7x to the fifth minus 3x to the fourth plus 2x plus 1. And again, the degree is odd, so the leading term is 7x to the fifth. Degree is odd, and a sub n is greater than 0, positive. Okay, so then you got to think, okay, degree is odd, and what are the ends doing? So the left end is going down, the middle we don't know, and the right end is going up. Okay, so that's the end behavior. So the left end is going to negative infinity, the right end is going to positive infinity. Let's do one more. F of x equals negative 4x to the fifth plus 2x to the third minus 7x plus 5. Okay, so degree is 5, which is odd. The leading coefficient is negative 4, which is negative. So that's flip-flops from the one we just did. So the ends are doing, so the left end is going up. And again, we don't know what's happening in the middle, and the right end is going down. Okay? So that's all there is to it. So we're just adding some pieces of the puzzle for graphing. All right? So the first thing we can identify is what are the ends doing. So we use the leading term test to tell us what the ends are doing. And it's one of the 4 cases. Here, let's do the last one. F of x equals x to the fourth plus 3x. Okay, so minus 7. So degree is 4, which is even. And the leading term is, leading coefficient's positive 1. Okay, it's positive, so that means both ends are going up. Again, in the middle, we don't know what's going on. Not with that test. We can tell with other things, but okay. So right now, the leading term test just tells us the behavior of the ends, the left end and the right end. Okay? So if the degree is even, like A and D there, both ends either go up or down. And again, I think of a simple case, x squared, and x squared parabola opens up if it's positive, opens down if it's negative. And that's true whether it's degree 2, degree 4, degree 6, any even degree, it's gonna, both ends will go the same direction. And then odd ends, one goes up, one goes down. And again, if it's, I think of the simple case y equals x cubed, and I mimic those ends. Okay? Okay, so now the next piece of the puzzle when we're graphing polynomial functions is you're going to find the zeros. And the zeros are the x coordinate of the x-intercept. So if I asked you to find the x-intercept So find the x-intercept of the graph of f of x equals x squared plus 6x plus 5. And if you recall, to find x-intercepts, you're going to find the zeros of the function. Okay, you're going to let f of x equals 0 and solve for x. Alright, so basically find the zeros of the function. Okay, so we're going to take the function f of x, which is x squared plus 6x plus 5, set it equal to 0, and solve it. And if you recall, for this we're going to factor the 5 that add to 6. So x plus 5 equals 0, or x plus 1 equals 0, so x equals negative 5, or x equals negative 1. Okay, so the zeros of the function are negative 5 and negative 1. Okay, now the x-intercepts of the graph is negative 5, 0, and negative 1, 0. Okay? So now we're getting another picture of the graph. Is we know that from the leading coefficient test, we know, so no, this is where we're headed with this. So from the leading coefficient test, we know that it's an x squared, positive, so even degree, so the ends are going up. The ends are going up. And we know that the x-intercepts are negative 5 and negative 1. So we know that part so far. So what's going on in the middle, we don't know quite yet. I mean, we do because it's a parabola. But basically, we're going to get this kind of thing. And then we just got to figure out where the bottom is. So the bottom, we still got to do other work. Okay, so now we're just adding that extra piece to this puzzle. So if you find the zeros of the function, that tells you the x-intercepts, right? That's a 0 of the function. That's a 0 of the function. Okay, so you find the zeros, so you know where the x-intercepts are. Find the zeros of the following function. G of x is x plus 1 times x minus 3 squared times x plus 2 cubed. And if I factor this all out, I'm going to set each, to find the zeros again, I'm going to set the function equal to 0. So I write the function down. I got it all the way factored out. So I'm going to get x plus 1 equals 0, x minus 3 equals 0, x minus 3 equals 0. Now the repeats I don't have to do, right, because they're not going to give me any new answer. So it's kind of redundant to do it all the times. But it's important to understand that we have them multiple times because it gives us some information. So plus 3, plus 3, plus 3. So x equals 3 twice. And x equals negative 2 3 times. Now when I write the solution set, if I was solving this equation for the zeros, I just write negative 1, 3, and negative 2, and you don't write the repeats. Now again, it's important to know that you have repeats because it gives us information about the x-intercept. So if I were to look at the graph of this, the degree is 6 if I were to multiply it out and leading coefficient be positive. So I would know that the ends are both going up from the leading coefficient test. I'm used to saying coefficient, but leading term test. I know it crosses at -1 and at -2 and at +3. Okay, and because I can know that -1 happens once, that gives me information. -2 happens 3 times, and basically what that tells me is that I'm going to cross through the x-axis. At -1, I'm going to cross through the x-axis. And at 3, I'm going to get a bounce. So now what's happening in here, I don't know, right? In between those spots, how low it's going. But basically, I know it's doing that. Something to that effect. Now again, I would have to do other work to figure out how high this part goes. I can figure that out pretty easily, actually. And anyway, so all I want you to know from right now is the leading term test tells us the ends are both going up. And then the zeros give us the x-intercepts, -2, -1, 3. Now, how did I know whether this went through at -2 or bounced at 3? And what that is, that's called our multiplicity. So let me define those for you. Okay, so the number of occurrences of zeros in a function is called its multiplicity of I should say of a particular zero. Okay, so the number of occurrences of a particular zero in a function is called its multiplicity. Or you can think of it as in factors. In factor form, basically the power, the number of times you get that power. So if you look at the original function, you have x plus 1 once, so the multiplicity is 1. X minus 3 twice, so the multiplicity is 2. And x plus 2 happens 3 times, third power, so it happens 3 times, so its multiplicity is 3. Okay? So we get -1 with the multiplicity for zeros, multiplicity, let me write it this way, 0 and multiplicity. So for -1 had multiplicity of 1, 3 had a multiplicity of 2, -2 had a multiplicity of 3. Okay? So multiplicity is the number of times it happens. Okay, so this is the thing that I just was doing on the graph. Even an odd multiplicity. So the idea, even an odd multiplicity, is if the multiplicity, if c is a zero of the function, so for example 3, if c is a zero of the polynomial function and has a multiplicity of k, so my example above, if c is 3, so that's the 0, and it happens twice, so the multiplicity is 2, which is even, I read this first line here, k is even, then the graph is tangent, and I like to say bounces, at c0 on the x-axis. So at 3, since there was an even multiplicity, it bounced. Now it can bounce from top or it can bounce from the bottom, so you kind of have to keep track where you are, and I'll show you in a little bit. Now if the multiplicity is odd, if k is odd, that's the bottom line here, then the graph just goes through at the x-axis. It crosses it, okay, at that point. So for instance, at -1, multiplicity is 1, and we see it went through. And for -2, multiplicity is 3, which is also odd, so it goes through. Okay, so it goes through at -2, goes through at -1, and it bounces at 3. Okay, so let's try an example. Find the zeros of the polynomial function and state the multiplicity of each. So remember, to find the zeros, we're going to set it equal to 0 and solve it. So we're going to, it's factored, that's the hard part, so that's done for us. And you're just going to set each of these equals 0, and you don't have to show all the work. Just change the sign, so x equals +4, because we're going to do x minus 4 equals 0. Add 4 to both sides. Subtract 1 to both sides. And then the multiplicity for negative 5 is 3. Multiplicity for 4 is once. And the multiplicity for negative 1 is twice. And that's it. Well, that's all there is to it. Okay, let's try another one. X cubed, x plus 3 squared, x minus 7 to the 4th. Set it equal to 0. So x equals 0. X plus 3 equals 0. X minus 7 equals 0. So we get x equals 0, negative 3, and positive 7 with multiplicity 1. No, that one's 3 because that was x cubed. And then we have x plus 3 twice, so that's twice. And then 7 is 4 times. Okay? Okay, so this one, x to the 4th, we gotta factor it and set it equal to 0, so that'd be x squared minus 9, x squared plus 1 equal to 0. Oh, they're both minus, sorry. And then this is x plus 3, x minus 3, x plus 1, x minus 1. So x equals negative 3, x equals 3, x equals negative 1, x equals positive 1. All of them have a multiplicity of 1. Okay? Alright, so that concludes the lesson for 4.1. Go to my math lab, complete your exercise there, and I'll see you next time.